Okay, so we've learned now how to draw pseudo-random draws from the uniform distribution. They're not IID draws, but they're pseudo-random in the sense they're almost IID draws. And then in the last video or the last lecture, we also learned then how do you use these uniform draws to get draws from some discrete random variables, from from some discrete distributions. One of them was the Bernoulli distribution. We used that as a motivating example to talk about the inverse transform method. And then we discussed the inverse transform method a little bit more specifically. And we realized that yes, given essentially any discrete random variable, we can generate samples from that using pseudo-random uniform draws, no problem, right? We can do it for Poisson, we can do it for Bernoulli, binomial, any probability mass function, any random variable with a probability mass function, and we can use the inverse transform method to get samples from it. So then why do we need to learn about any other technique? And the reason we need to learn about another technique or it would be useful is the last point that we had discussed. The last point that we discussed for the Poisson random variable, we discussed that, because there are infinite possible values a Poisson random variable can take, it can be quite expensive to generate samples from a Poisson random variable because you could get stuck in, what could be an infinite sort of loop. Particularly if you don't choose where to start from in a smart way. And so that's really why there is a need to maybe look at another type of method of drawing random variables. And that method is the acceptance rejection technique. Now, for discrete random variables, this technique is not very popular. It's not used very often, but for continuous random variables, it is very popular. Okay, and so we're going to go through this pretty carefully, and it'll be a slightly technical lecture because you're also going to see some theory and some proof in this as well. Okay, so like I said, although we can draw from any discrete distribution using the inverse transform method, we can imagine distributions on where there are countably infinite points that you could go to, like Poisson, which takes value 0, 1, 2, 3, and so on. The inverse transform method can be quite expensive. So we're going to do acceptance rejection. So what is acceptance rejection? So consider Pj to denote the PMF of the target distribution, which Pj basically denotes that the probability x takes the value Aj is small pj. Okay. And similarly, for these same states or values Aj, let Qj denote the PMF of another random variable, another distribution, and that's a random variable y, which takes masses Qj. So the probability that y is equal to Aj is Qj. Okay. Now, suppose that you can efficiently, right, efficiently being the key, you can nicely and efficiently draw samples from the mass function of Q. So you can draw from Qj, but you want to draw from Pj. You don't want to draw from Qj. You actually want to draw from Pj, but Qj is what is available to you. Okay. And if that is so, then what we can do is we can use the draws from Qj to actually get draws from Pj. Right? We can use draws from one random variable to draw draws from another random variable. This can be done if two things hold. The first one I'll talk about, and then right now, and the second one a little later. So let's suppose that there is a constant c that is finite. There's a finite constant such that if I look at the respective mass functions under my target mass function Pj and my proposal, so this is the proposal mass function Qj, if Pj by Qj is less than equal to c for all j where Pj's are positive, so I take all the states where my target mass random variable takes mass. Those are all the Pj's where Pj's are positive. Okay. And if I look at the ratio of Pj and Qj, so this basically, this thing over here is the probability that, probability that x takes a value aj divided by the probability that y takes the same value aj, right? But then this aj is such that pj is greater than 0, so that this numerator is actually positive, right? So that's what this is saying. But I suppose now that for all the j's, pj by qj is bounded. So pj by qj is bounded by something finite. Okay. If this holds, then if we can find such a qj and the corresponding c, then we can implement an acceptance rejection technique, or what I like to call an accept reject sampler. And the idea is the following: you draw samples from qj and accept these samples if they seem like they are likely also from pj. Okay, so you draw from the proposal mass function, and if you draw from it and you say, oh, okay, you know what, this value seems like it could also be from pj, you accept that value. So how does this technically work? This is the algorithm. You draw a uniform draw, like you will keep seeing that drawing from the uniform random distribution is going to be something we're going to do every single time we need to draw from any other distribution. So you get a uniform draw, and suppose that we can obtain a value small y from the distribution with probability mass function qy. Okay, so we simulate y from q. So this is what is going to be called our proposed value. Okay, so this is our proposed value. Now, if for our proposed value, if u is less than equal to py by c qy, okay, if this holds, then so this ratio basically is the following. This is the probability that x takes the value y divided by c times the probability y takes the value y, right? Okay, so now if this holds, now, then we return x equal to y, right? So if this condition holds, if the uniform draw is less than equal to the probability that x takes the value y divided by c, and also divided by the probability y takes the value y, small y, then I return that x is y. So I say that the proposed value is very good. Else, and also I stop. As soon as that happens, I say, okay, great, I've gotten my value. I don't need to do anything else. But if that doesn't hold, then I go to step 1, which is the act of drawing again from the uniform draw. So in this way, I sort of can keep looping the algorithm until I get inside step number 4, until u is less than equal to py by c qy. Okay, this is the idea. Okay, this is the idea of the algorithm. Now, why does this make sense? Why does this algorithm, when it stops and it returns x equals to y, why will it give good values for our desired target distribution? So understand also that if I propose a value y from q that is not a good value, then that gets thrown away. We are not going to accept it. It doesn't like that value won't be accepted. The loop will start again, a new uniform draw is simulated, and then a new proposed value is simulated. And now we'll see whether this new value looks good or not. Okay, so let's actually see how can we understand that this actually works. So the theorem that we're going to look at is that the accept-reject method, the theorem statement is that the accept-reject method truly generates a random variable with probability pj, with probability x equal to aj being exactly pj. And this is my desired distribution. Right? And the theorem says that, yeah, the accept-reject method will give you a random variable that takes a value aj with probability pj. But further, notice that it requires a few number of iterations before it can actually accept. And we'd like to know how many iterations will it keep on looping before it gets inside line 4. So further, the number of iterations needed to generate an acceptance, okay, so the number of loops needed to generate an acceptance is distributed as geometric 1 by C, where the C is the same C as we saw before. Okay, so let's look at a proof of this. So what we'll do is we'll actually prove the second statement, this statement first, and then we'll go back. So first we look at the second statement. We note that the number of iterations required to stop the algorithm is clearly geometrically distributed. With what probability of success, I don't know. But it is geometrically distributed because the algorithm loops until something happens. So the number of time it loops is distributed in the style of the number of Bernoulli trials needed to get one success, right? Which is exactly what a geometric random variable is. A geometric random variable counts the number of trials or attempts needed to get one success, or at least one kind of geometric random variable. And this is exactly what the situation we have. So the number of iterations is definitely distributed geometrically, but with what probability of success is what we need to find. So let's start there. So now we need to show that the probability of success is 1 by C, where success here is acceptance. So we want to show that the probability of accepting in any given iteration is going to be 1 by C. This is what we want to show. So let's take a look. So first what we do is we look at the joint behavior of Y's and U's. Now let's understand one thing. What are the random quantities in my algorithm? So if I go back to my algorithm, there are a few random quantities. There is the U's which are random, and there are the Y's which are random. Both the U's and the Y's are random, which means when I talk about probabilities of anything, I want to understand is the probability with respect to the randomness of the U's or the randomness of the Y's. Okay, so we have to be careful about that. So if I look at the joint probability of Y being equal to AJ, so that means that actually proposing a value, any value AJ, and also accepting the value, right? So I want to look at the joint probability, that what is the probability that I proposed a value AJ and then also I accepted it. But I can write any joint probability as the product of the marginal probability times the conditional probability, right? So conditional of the first event given the second event times the marginal of the second event. Okay, so that's okay. But now what is the probability that Y equals a value AJ? Now this is just a question about Y, right? Now Y is distributed according to the probability mass function Qj. So this value is nothing but Qj. Okay. And now given that Y is equal to AJ, I'm looking at the probability of acceptance. And I accept only when U is less than equal to Pj by C Qj, right? Right? And so this is equivalent to saying the probability U is less than equal to Pj by C Qj, where these are now, just numbers. But then I know that this probability, I know very well because I know what a CDF of a uniform distribution is, uniform random variable is. And so this is nothing but Pj by C Qj. Now I have my Qj and the Qj's get cancelled. And so this becomes Pj by C. Okay, so I get that the probability of proposing a value AJ and accepting it is equal to Pj by C. But this is not what I want. I just want the probability of acceptance first. So if I just want the probability of acceptance, but I have the joint probability of proposing and accepting, then I just want to look at the marginal probability of accepting, which means to look at the marginal distribution or the marginal probability. I can then sum over all the possible values I could have proposed from Y, right? So the marginal is just the sum over over the joint. And so the probability y is equal to aj, and except I'm summing over all possible j's. But this I know is nothing but pj by c. And so I get summation j pj by c. But now this is nothing but 1 by c summation pj. But because pj's form a valid probability mass function, summation pj's are 1, and so this is 1 by c, since summation pj's is equal to 1. Right? So thus we have that that our second statement, that what is the probability of what is the distribution of the number of loops, is geometric 1 by c. Okay. Now let's get back to the actual first statement of the theorem, which is the probability that x takes a value aj is pj. Right? That's what we want to look at. We've done actually half the work for this, because now if I want to look at what is the probability x takes a value aj. Now x here is what is returned by the algorithm. So let me write that down here. So this x over here is what is returned by the algorithm. And I want to show that what is returned by the algorithm, it has exactly the same structure or the same probability mass function as my desired probability mass function. Okay. Okay. So now the fact that probability x is equal to aj, well, how can my algorithm return aj? Well, my algorithm could return aj if it exited out of the loop in the first attempt and aj was what it accepted, or it accepted aj in the second attempt, or it accepted aj in the third attempt, or it accepted aj in the fourth attempt, and so on and so forth. So the ways that x can take the value aj is the sum over all possible n's, where probability aj is accepted on iteration n is what I'm summing over. Right? So I'm summing over the probability aj is accepted on iteration n. Now this n could be the first iteration, the second iteration, the third iteration, and can go up to infinity. You can be stuck in an infinite loop maybe. Okay, but if aj is accepted on iteration n, then that means that all the n minus 1 iterations, there were no acceptances. Okay? Not that aj was not the acceptance, but there were no acceptances at all. Right? Because if there was a single acceptance, we would not be on loop n. So this becomes probability that there's no acceptance until iteration n minus 1. But now in the current iteration, the only way to accept aj is to propose aj and then to accept it. Right? Now this we've already calculated to be pj by c, so that's easy. But no acceptance until iteration n minus 1 happens with probability 1 minus 1 by c. Because there is a probability 1 by c, the probability of an acceptance is 1 by c. So the probability that there is no acceptance is 1 minus 1 by c in any iteration. But now this has to happen in all of the iterations, including iteration n minus 1. So that means I have summation n going from 1 to infinity, 1 minus 1 by c to the power n minus 1 times pj by c. Okay. Now, it can be shown via some geometric sum calculations, which I don't want to get into, fairly straightforward, that this sum is just c, and this is independent of n. So this just becomes c, and c will get cancelled, and so I just get pj, which means the probability x is equal to aj is pj, and then that completes the proof. Okay, so we are able to show that if we take a random variable of interest x, which has some sort of mass function pj, if we propose from a qj, okay, that is a proposal distribution that's fairly well behaved, then I can, using those proposals, if I just use the correct type of algorithm, I can actually get draws from QJ. Right. So now that we've understood hopefully the proof, let's also take a look at the second statement in the proof, second line in the statement of the theorem, which said that the number of iterations needed to generate an acceptance is distributed as geometric 1 by C. Now, this is actually very important because what this tells us is before running the experiment, or sorry, before running the algorithm, I have an idea on the kind of behavior I expect from the number of iterations. So if I know C and I need to know C to implement the algorithm, then I also know that since the probability of acceptance in any given loop is 1 by C, then I know that the expected number of loops of one acceptance is C, because this, if X is distributed, so let me not call this X. So if Z is distributed as geometric 1 by C, then expectation of Z is C. Right? So that means if the number of loops is distributed as geometric 1 by C, then the expected number of loops for one acceptance is C. So if C is really large, if the upper bound on Pj by Qj, so remember C is basically the maximum value that Pj by Qj can take, where the maximum is taken for J such that Pj is positive. Right? This is what C is. If this maximum is really large, then I may have to wait a really long amount of time to get one draw. All of this is to get one draw from my target distribution. Okay, so that can be quite inefficient. So C basically tells us how efficient the algorithm is. The smaller the C, the better it is. Right? So smaller the C, the better it is. Another important thing is, recall when I write this, that J such that Pj is greater than 0, I'm inherently also considering the following structure, and that is to note that the support of AJ, the support that is AJ, which is all the states that take positive mass under my target distribution, for all of those states, the proposal distribution must always be positive. The idea is that if there is a value that the proposal can never propose, then the algorithm can never work, right? So if there is a value under my target distribution that the proposal distribution can never propose, then I will never get the algorithm to work, right? Because that value will never be proposed. If it's never proposed, it can never be accepted. Okay, so which means that for all Aj in the support of Pj, okay, probability that Y is equal to Aj, which is basically my proposal mass function, that has to be positive for all those Ajs that for which Pjs are positive. Right? So simply, the proposal distribution must have either equal or larger than the support of the target distribution. Okay.